Hi, my name is Walter Geckelman. I'm in the physics department at UCLA, and my specialty is plasma physics. Now, to introduce my little talk, I'd like to show a satellite picture of the world with the clouds removed. It's taken over many days, and at night, and one can see quite clearly who's using all the electricity on the planet. Basically, Europe, the United States, and Japan is lit up like a Christmas tree, and enormous regions of the Earth are dark. Now, the problem is illustrated in this second graph, which is a little old, but shows essentially the standard of living, which is called the Human Development Index, but they're equivalent, and the per capita electrical usage for many, many countries in the world. And this is the use per capita electrical usage seems a lot. For example, in the US, it's 12 kilowatts hours. And you might say, well, I don't use 12,000 watts day and night. But of course, this also includes the infrastructure that supports you being here, namely roads, buildings, air conditioning, and everything you use in your daily life that took energy to build and will take energy to dispose of. One thing you could see is that, very roughly speaking, the standard of living is nearly directly proportional to per capita energy consumption. What does that mean? It means for many developing countries with large populations, if for them to get up to the same per capita usage of someone in the US or Japan, the world has to produce far, far more energy. And in fact, it's very questionable whether that energy is there or ever will be. Now, this is one of the applications of plasma physics, thermonuclear fusion. This is very far away. Unfortunately, it's been very far away for quite a number of years, because in order to do it, you have to make a plasma of 1 to 200 million degrees and sufficient density so that you can get hydrogen to fuse to become helium, and you get energy out, enormous amounts of energy. Now, in order for the world to sustain the energy usage that it will demand in the future, one can't really use oil because we're nearly out of it. Coal is really not a great option. And anyway, there's a couple centuries of coal left, and that's it. And we're talking about our species for years to come. And by best estimates from experts in this area, alternative energy such as solar energy, tidal energy, and so on, could only at best provide 15 to 20% of the world's power. At the moment, it's 0.5% is coming from renewable energy. So where's the other 80 to 85% coming from? It's either going to be nuclear fission, which has its attendant problems, or fusion, which is probably 100 years away. But if fusion is successful, it would solve the energy problem completely, forever. Now, plasma physics has many, many other uses. For example, all semiconductors, transistors, computer chips, and so on, all of them are processed in plasma devices called tools in large fabrication plants, none of which, by the way, are in the United States. And our entire industry involving computers, cell phones, and communications completely depends upon this. So one might say, in fact, so civilization as we know it depends on semiconductors. They're all made in plasmas. Plasmas can also be used for the other uses listed below. For example, lighting is huge. Plasma TVs, LCD TVs have plasma lights to illuminate them. Projectors, street lighting, and so forth all use dense, very small plasma sources for them. In fact, it's been estimated that about 14% of our entire economy the United States' economy, is in some way tied to plasma physics. By the way, it's also used to waterproof all fabrics. It's used to make, in the making of all artificial joints, jet engines, and so on. Now, that brings us back to education. Now, I know that presently there is a package on the table, which was approved. We'll see what happens, in which there'll be an injection of cash to try to help the infrastructure of science and universities, sorely needed, because grants, for example, the National Science Foundation, which is one of the greatest sources of university support for not only plasma physics, that in the Department of Energy is, but for many, many other branches of science and mathematics. A typical grant size in plasma physics hasn't changed in 10 years. In fact, the number is closer to 20 years, about 100,000 a year. That might have been fine 20 years ago, but nowadays it's woefully inadequate to support research. A graduate student costs to support them about 50,000 a year. That's for just one person. Laboratory instruments can easily cost that or twice that. So the price of grants has not at all kept up with what it costs to do research. So this has discouraged people. In fact, now the success rate for scientific proposals in the National Science Foundation in plasma physics is only 10%. 1 out of every 10 proposals are funded. So a lot of people have just dropped out of the field because it's very, very hard for them, if not impossible, to get funding to do their research. And so this is not being taught. Students see this and they don't want to enter science, not only plasma physics or anything else, because there won't be jobs for them. And if they do go into universities eventually and want to do research, they're facing a huge struggle, very big uphill struggle, to try to keep their effort funded. And they have to write multiple proposals and hope that 1 or 2 of them are funded, which is very time-consuming and no fun at all. There are far more people that have dropped out of plasma physics than there used to be, and in the field, there are very few decent-sized groups doing basic plasma physics research in the United States. And that means that we are losing, or we may have already lost, our unquestionable leadership position in plasma physics. We've had that position since the birth of the topic in our 1920s to 30s, but now other countries that see the need, for example, for fusion and support for industrial plasma processing research, and these countries are, as listed, Europe, for example, Italy, France, both Germany, some Soviet Union, and so on, are investing heavily in this. The Nordic countries are, Scandinavian countries are. Japan's plasma budget is many times ours per year, and South Korea and China are now building machines that are much larger than anything in the United States. And so it's great that there's a stimulus package, but in the future one must consider that this field and all of science has to be continually nurtured. Essentially, all the United States has left, since we're not a manufacturing country anymore, is its technology. And when we lose that edge, which will happen if research at universities collapse or dwindles to nearly nothing, then what do we have left? Nothing to export except perhaps some food, and nothing to sell except for recycling some real estate.